Hello everyone and welcome to Instant Biology by Dr. Neelab. The topic that I am going to start today is infrared absorption spectroscopy. So for those of you who have been following me since past, they would be knowing that I have made a playlist on analytical techniques, and in that playlist I have already uploaded videos on spectroscopy. So this particular video would be an addition to that series on the analytical techniques, and I would be talking about infrared absorption spectroscopy in this. So without much ado, let us start talking about today's topic. So when I say infrared absorption spectroscopy, what does that mean? So if you have seen the electromagnetic radiation spectrum that is over here, if you see this, then you can see that on the x-axis you can see the frequency that is present in the hertz, right? If you see over here, this is the frequency written in the hertz, and right from 1, this is 1, and it is increasing 10 to the power 5, 10 to the power 10, 10 to the power 15, 20 and 10 to the power 25. Okay, and over here you can see the wavelengths, right? So wavelength is written in centimeters. So you can see that the visible region lies somewhere around 10 to the power 15 frequency over here. This is the region where the visible light falls, and if you focus just below the visible light, you can see the infrared rays over here. Okay, so these are the infrared rays. That means the frequency of the infrared rays is lower than the frequency of the visible light. If you go on the upper side, then UV light is present. That means just above the visible light, or the higher frequency end to the visible light, is ultraviolet light. Okay, so that means just lower in frequency to the visible light is present the infrared region. Okay, that means we can define the electromagnetic spectrum for the infrared region to be around 1 micrometer to 100 micrometers. Understand this, that this value actually varies from books to books. Okay, so it varies, so you do not need to be specific about the values. You just need to understand what is the position of the electromagnetic radiations with respect to the other different types of radiations on the electromagnetic radiation spectra. Okay, next important feature is that you can divide the infrared region into 3 parts: the near infrared, the mid infrared and the far infrared. Understand this, that this near, mid and far is with respect to the visible region. I have written over here also that the region that is more near to visible region, that would be called as near infrared. The region that would be farther from the visible region, that would be called as mid IR, and the region that is the farthest would be considered as far IR. So if I draw like this, so this suppose is the visible region, this is the visible region, just next to the visible region would be the near IR, following this would be the mid IR, and farthest from the visible region would be far IR. This is the scenario. Okay, and you can see that the wavelength is decreasing like this. The frequency is decreasing like this. So this frequency decreasing from up to down. Okay, I believe you would have understood this and understood the classification of infrared region into near, mid and far IR. Okay, now this might be a long video, but we would be covering everything in this one particular video. So this would be kind of a one-shot video, so please watch this video to the end so as to clear your doubts about this particular topic. Let us now talk about the frequency. When we say frequency of infrared rays, what do we mean? So you would be knowing what does frequency means. Frequency is the number of wavelengths that pass a particular point per unit time. Okay, so if I say some point is present, if I say this point, then the number of wavelengths that are passing per second of this point is called as frequency. Okay, frequency is always with respect to time, understand this. Over here we are talking about the number of wavelengths. Okay, if I'm talking about the heartbeat, then I can say that the frequency of heartbeat is this. That means how many times it is beating per time or per unit of time. Okay, so frequency can be of anything, but over here we are talking about the infrared regions frequency. Okay, now let us move on to the next point, that if I'm talking about infrared radiation absorption, that means if this is a molecule or if this is a body and this is the infrared radiation that is falling on it, so it is not like that this particular molecule can absorb any infrared radiation. There is a selected frequency. Only if the infrared radiation is carrying that frequency, only then it would be absorbed by this molecule. Okay, so that is why I have written over here that a molecule absorbs only selected frequency. It cannot absorb all different types of frequencies of the infrared radiation. Only selected frequencies, only particular type of frequencies would be absorbed. Next, absorption leads to change in the energy. What does this mean? Suppose this is an object, and if a infrared radiation falls on this object, now this object would be having its own energy, right? This object would be having its own energy, energy 1 suppose, and after the exposure to the infrared radiations, what will happen? The energy would change. Basically the energy would increase, and there has been seen or observed that the change in energy is of an order of 8 to 40 kilojoule per mole. Okay, this is the change in the energy that is observed when the infrared radiations come in contact with the object or a molecule. Okay, next, this infrared radiations are not very strong in energy. That means their energy is not very high. Why their energy is not very high? Because you would be knowing that there is a formula of E is equals to hc by lambda. Now this means that lambda or wavelength is inversely proportional to energy. That means when energy is increasing, lambda is decreasing, or vice versa. You can say that when lambda decreases, energy increases, and when lambda increases, energy decreases. Now over here you can see that this is the wavelength. Over here this is the wavelength, and this wavelength is increasing downwards. If you see over here, this in this particular direction, lambda is increasing, wavelength is increasing, and as I said, if the wavelength increases, then energy automatically decreases. That means infrared radiations have very less amount of energy. Now if they have less amount of energy, they would not be able to cause electronic transitions as can be attributed to the UV radiations. Okay, why? Because those radiations are very high in energy. Suppose this is the ground state, these are the high level states. Okay, so suppose this is a molecule over here, and when the infrared radiation falls, it cannot move to the higher levels. Moving to the higher levels would not be possible. Why? Because the energy is very less, and it can only support bond vibration. The only is this much only, the energy is this much only, it would be able to support bond vibrations only and not electronic transitions. So always remember that IR cannot support electronic transitions, it can only support bond vibrations, right? So I believe you would have understood this concept at least. Let us move forward and talk about the next thing. Okay, so coming to the next point, what is the physical basis of infrared spectroscopy? Why does infrared spectroscopy occur? So first of all, let me tell you that infrared spectroscopy is a type of vibrational spectroscopy. It does not involve, as I said, it does not involve electronic transition, does not involve electronic transition. It does not involve that. Why? Because the energy is less. Understand this, that if I have a molecule, suppose this is the let us say that this is a molecule A, it is connected with B, over here C is present, over here D is present, over here E is present, and in this way they are connected, these atoms are connected. Okay, these atoms are connected, and suppose this is a molecule, these all are atoms. Okay, now these atoms form a molecule. Understand that all the bonds within a molecule vibrate. What does this mean? So this bond between A and B would vibrate, this between A and C would vibrate, between A and D would vibrate, and between A and E would also vibrate. That is why, or that is what is written over here, that all the molecules, all the bonds present inside a molecule would vibrate. Okay, why vibrate? Because of the normal or the original amount of energy present inside the molecule. This vibration would be just because of the original amount of energy present inside the molecule that causes vibration. It has nothing to do with the infrared spectroscopy as of now. I would be connecting it later on. Okay, so these vibrations can be of two types. Understand this, that the vibrations can be of two types. What are the two types? One is the stretching vibration and one is the bending vibration. What does stretching means? Suppose I am talking about A and B, so they are connected by a bond. So this vibration can be in this direction or they can be in this direction. That means they can be compressing or they can be extending, compressing, extending, compressing, extending, compressing. So this is basically what is called as stretching vibration. Okay, this is what is called as stretching vibration. Now if I talk about bending vibration, now suppose this is C, this is A, this is B. Now this A can move this side also, can move this side also, this B can move this side also, can move this side also. This is called as bending vibrations. Okay, that means movement like this, or changing the angle of the bond. If A or B move in this direction or in this direction, definitely the bond angle, the bond over here, the angle would change. This causes bending. Okay, this is the reason of bending. So if I try and define what is stretching, so stretching occurs along the line of the bond. So this was the line of the bond, remember, A to B, this was the line that is connecting A and B. So the stretching occurs along the line of the bond, this way or this way, this way or this way. This means compression, this means extension. Okay, so this is stretching. If I talk about bending, bending does not occur along the line of the chemical bond. So suppose this is the line of the chemical bond, it will not occur along the line, but it will cause bending. It can move like this, can move like this, can move like this, can move like this, like this. Okay, so this is the example of bending. Now let me just show you with the help of a proper example. Suppose I am talking about a bond called as CH bond, carbon hydrogen bond. Okay, carbon hydrogen bond. So I am considering the stretching vibration only as of now. I would be talking about the bending vibrations later on in this particular lecture. So if I talk about stretching bond vibrations, if I talk about stretching bond vibrations, so over here you can see that carbon hydrogen bonding is present over here. Carbon hydrogen bonding is present over here. And when I talk about vibration frequency means the frequency with which the vibration or the bond is vibrating, because we are considering the stretching bond vibrations. So along the line of the bond, what is the vibration? If I am talking about the stretching bond vibrations, what is the frequency of the vibration? So suppose the frequency of the vibration is 9 into 10 to the power 13 per second, right? Suppose this is the frequency. Now understand this, that this particular bond or this particular molecule or this particular entity would absorb the the infrared radiations only when the incoming infrared radiation has a frequency of 9 into 10 to the power 13 per second. That means the incoming infrared radiation needs to have the same frequency as that of the vibrating bond. Understood that? I believe you would have understood that. I mean to say is that there should be same frequency of the incoming infrared radiation that to the vibrating molecule, the frequency with which the molecule is vibrating. Okay. So when these frequencies are identical or they match, only then the energy is transferred. From where the energy would be transferred? The energy would be transferred from the incoming infrared radiation to the vibrating molecule. Okay. So what would be the result if the infrared radiation is absorbed? What would be the result? The frequency as well as the intensity of the bond vibration both will increase. Frequency will also increase and intensity of bond vibration will also increase. Intensity means it would be now vibrating more intensely. Frequency would also increase. That means the number of times that it was vibrating would also increase. In other words, we can say that the amplitude would increase. That means if you consider a peak, suppose this was the peak that was previously forming, now the peak length would be somewhere over here. So this is the difference. This is the this is the result of the infrared radiation falling on a molecule and the energy being absorbed by the molecule from the infrared radiation. That is, the frequency will increase and the amplitude of the vibration will also increase. Now the energy would not always be absorbed, it cannot be contained in the molecule forever. So what will happen? This molecule will sooner or later release this energy. Okay. When the molecule releases this energy, the bond returns to its original parameters. That means whatever parameters or whatever frequency with which it was vibrating, it returns to the original frequency. Remember that after the infrared radiation falling on this molecule, the frequency had increased, but now it will return back to the normal because the energy has been liberated. Okay. I believe you would have understood this much. Let us move forward to the next topic. Okay. Now understand this, that different bonds have different vibrational energies. You would understand this simply because there are different atoms are involved and there are different reasons behind this. But for now you should understand this, that different bonds would have different vibrational energies. There would be different vibrational energies. And when the vibrational energies would be different, definitely they would absorb different infrared radiation frequencies also, because if the vibration energy would be different, it would be absorbing only that frequency that would be coinciding with the infrared. I mean to say, if the infrared radiation has a frequency that is similar to this bond vibrational frequency, then only it will be absorbed, otherwise it will not be absorbed. That means different bonds will have different vibrational energies. Also understand that all bonds cannot absorb infrared radiations. Now all molecules have bonds, right? I mean different atoms are connected with bonds. But understand this, as I have previously said also, that they are vibrating, but it is not necessary that all bonds can absorb infrared radiations. Some of them cannot absorb infrared radiations. We would talk more about them. So what is the requirement? When can we say that a bond would absorb infrared radiation or not? So the requirement is that there should be a dipole moment that must change during vibration. See, I told vibration is important, but along with the vibration, the dipole moment that is present inside the bond should also change. If it is changing, only then you can say that it might absorb infrared radiation. If it is not changing, if it is permanent, then you can say that it won't absorb infrared radiations. Now let us talk about dipole moment. So dipole moments are present in polar chemical bonds. You would be knowing that. What is polar? Polar basically means that when a higher electronegative atom is bonded to a lower electronegative atom, suppose there is A and B. Suppose A is highly electronegative, B is electropositive. So what will happen? There are some partial charges that are present on this. So it has partial negative, it has partial positive. And now since there has developed a pole, negative pole and positive pole over here, therefore we are calling it as dipole, right? So what I have said is that the dipole moment must change during the vibration. Dipole moment must change during the vibration. Okay, now let us move forward. If the polar bond vibrates with a particular frequency, bond dipole should also vibrate. This is obvious. If a bond is polar and it is vibrating, suppose it is undergoing stretching vibrations, so definitely the dipole should also vibrate, and when the dipole is vibrating with the same frequency, the dipole would lead to change, right? So magnitude, how can you calculate the magnitude of the dipole? The magnitude of the dipole basically depends upon two things. First is charge on each atom, and the second thing is bond length. What is the charge that is present on each atom? So over here we were talking about A and B, they had partial charges on them, and also what is the bond length? Okay, that means what is the bond length, whether it is a single bond, double bond or triple bond. If there is a triple bond, then the bond length would be less. If there is a single bond, then the bond length would be more. Okay, next, so when the bond stretches, I have already told you about the stretching vibrations. When the bond stretches, the bond dipole increases, and when the bond compresses, the bond dipole decreases, right? So this is vice versa. Understand this, that when the bond stretches, that means suppose this was A, B, when the bond stretches, this moves in this direction, this moves in this direction, the bond is stretching, and when it is stretching, the bond dipole increases, the bond dipole would increase. Now if frequency of the incoming radiation, is equal to the frequency at which the dipole is changing, then only the absorption will take place. What have I written? Understand this, that if the incoming radiation is coming, if this is the incoming radiation, okay, and there is a bond that is continuously changing the dipole, so what is the frequency with which the dipole is changing? If that frequency is equal to the frequency of the incoming infrared radiation, then this would lead to the absorption. Only then the absorption will take place. I believe you would have understood this. So let us move forward. So now let us talk about what is the capacity to absorb infrared radiation. Now as I have said, that if the dipole is changing with a particular frequency, then the incoming infrared radiation should have the same frequency, and only then the infrared radiation would absorb. Okay, so now I have divided the materials into two portions, one that are having the capacity to absorb infrared radiations, and one those do not have the capacity to absorb infrared radiations. So those that do not have the capacity are called as infrared inactive, and those that have the capacity to absorb are called as infrared active. Now let us understand, or let us talk about them in briefly. So the first thing is, let us talk about the infrared active components. So over here infrared absorption takes place, as I have already explained. Why are some bonds infrared inactive? Why can't they absorb? Because the molecular vibrations, they are not able to give rise to the infrared absorptions. The molecular vibrations that were taking place, they were not able to create a changing dipole. Okay, the bonds there was molecular vibrations, no doubt in that, but the molecular vibration was not able to create the change in the dipole. I told you that change in the dipole is essential. If the change in the dipole is not taking place, ultimately what will happen? There would be no infrared absorptions, and this type of components or compounds that are not showing infrared absorptions are called as infrared inactive. For example, H2, N2, O2. Now you can see that this O double bond O or N triple bond N, okay, or H2 What are these? These are diatomic gases, and what happens is there is no dipole. Okay, there is no dipole because they are the same molecules. The same molecules have attached. So even if they are stretching or doing something, they are not having any dipole. If they are not having any dipole, they would not absorb infrared radiations. Okay. Now understand this, that this is an important note. All molecules having permanent dipole moments are also not infrared active. What do I mean? That it is not necessary कि a molecule that is having a permanent dipole will be infrared active. It is not necessary. Why? Because I am continuously saying that there should be a change in the dipole, not permanent dipole. I do not want the permanent dipole. I want continuous changing dipole. So that is why I have written that the molecules that have permanent dipole moment, they might also not be infrared active. So the stretching and the bending should be able to produce change in the dipole moment, and only then they can be considered as infrared active. This is what I wanted to say over here. Okay, next, it is also possible for a molecule having zero dipole moment. Now this is also very important, that a molecule that is having zero dipole moment, it can also show temporary dipole moment due to specific molecular vibrations. Now let us take the example of CO2, carbon dioxide. Okay, let us take the example of carbon dioxide. Now you can see that this is C. Okay, this is CO2. Now the stretching can take place like this, and there can be bending also like this. Now if the symmetrical stretching takes place, now what does symmetrical stretching means? That means this oxygen over here and this oxygen over here, they are pulling the electrons from the carbon. Okay, this is what I wanted to say. I'll rub this off. They are pulling the electrons towards themselves, and carbon is having the slightly positive charge. But what I want you to understand over here is that if the symmetrical stretching is taking place, symmetrical stretching means when simultaneously both are pulling apart at the same time and with the same intensity, and both are coming back or compressing with the same intensity at the same time. This is called as symmetrical stretching. So this is going apart also at the same time, coming together also at the same time. This is called as symmetrical stretching. So when the symmetrical stretching takes place, then what happens is that both bonds are stretched and compressed at the same time to the same extent, and because of this, dipole moment would be zero. And as I have said that when the dipole moment will become zero, even after the vibration, then infrared inactive would be the status of that molecule. Infrared inactive would be the status of that molecule. Let us move forward and talk about the next case. I will come back to this diagrammatic representation in a bit, in the last. So under asymmetrical stretching, what happens under asymmetrical stretching? What do we mean by asymmetrical stretching? Understand this, that one bond is compressing and one bond is expanding, right? So if I draw it like this, then this is C double bond O. Suppose this bond is extending and this bond is compressing. Okay, so one is compressed while the other is stretched, then this leads to a change in the dipole moment, right? This leads to the change in the dipole moment. So you would understand that carbon dioxide is having a zero dipole moment if I talk about in general, but because of the stretching and bending, what happens is there is a temporary dipole moment under asymmetrical stretching conditions. Okay, so bending vibrations are also allowed here, but I won't be talking about them over here. Bending vibrations are also allowed, but over here, because I'm continuously talking about the stretching vibrations, so this stretching, asymmetrical stretching would lead to energy changes. this asymmetrical stretching would lead to the production of the dipole, or change in the dipole rather. Okay, it will cause the change in the dipole. Now let us move on to the next important point, and that is infrared spectra. Let us talk about infrared spectra. So infrared spectra basically has two important aspects. Understand this, that infrared spectra has two important aspects. Now what are these two important aspects? The first is, what is the position of the peak? That means at what wavelength is the peak present? This is the important thing. And the next thing is, this was the first thing, what was the wave number or the wavelength, at which wavelength the peak is present, and what is the intensity of the peak, basically what is the intensity and what is the wave number. That means wavelength. So understand that wave number is just the inverse feature of wavelength. Okay, so position of the peak and wavelength, these two are very important aspects of infrared spectra. What information does infrared spectra impart to us? So the information that it gives us is about the functional groups. You would be knowing about functional groups, right? So suppose carboxyl group or amino group or SH group. So what basically functional groups are present in a molecule, this information can be easily extracted from infrared spectra. Why? Because different functional groups absorb at different wavelengths, plus their peak intensity is also different. That is why I told you that it is basically, there are two aspects that I talked about. Now infrared absorption position. Now how much energy is involved in this bond vibration depends upon multiple things, right? That how much vibration would be there, or what would be the energy involved in the vibration of a bond, depends upon multiple things. Let us talk about those things. So the first thing that comes to mind is the strength of the bond. That means more is the strength of the bond, more vibration energy would be there. For example, there is triple bond, there is double bond, there is single bond. So you would be knowing that the strength of the triple bond is the highest, double bond is lesser, and single bond is the least. That means the higher the bond dissociation energy, stronger is the bond, and stronger is the bond, then more or high amount of energy would be absorbed by that particular bond. So we are talking about wave number over here. So you would be knowing that E is equals to hc by lambda, and 1 by lambda is equals to wave number. So when we talk about energy, so wave number is directly proportional to energy, and if I talk about wavelength, then wavelength is inversely proportional to energy. Now you would have understood this, that depending upon the strength of the bond, the energy changes. Okay, bond dissociation energy changes. So over here you can see that C triple bond O, C double bond O, C single bond O. There are three examples over here. In case of C triple bond O, the absorption takes place at 2143 centimeter inverse. Now in case of C double bond O, the wave number basically increases down to 1715, and it further lowers down at 1100 centimeter inverse. That means as the bond energy is decreasing, the wave number is also decreasing. That means the wave number at which the absorption is taking place, the wave number at which the absorption is taking place would be changing. Okay. Now let us talk about the masses of the atom involved in the bond. What are the masses of the atom involved in the bond? Understand this, that the vibrational frequency, okay, the frequency with which the vibration is taking place is depending more on the lighter object. Previously, in the previous example, what did we see? The vibrational energy was dependent upon the type of the bond. That means bond dissociation energy. That means triple bond or double bond or single bond. Triple bond had more vibration, right? Over here we are saying that vibrational frequency basically depends upon the lighter object than the heavier one. Okay, if you see carbon being attached to hydrogen over here, carbon attached to deuterium, carbon attached to oxygen, carbon attached to chlorine, you can see that in this particular direction, the lighter atom and the heavier, basically the heavier atom, the carbon atom is the same, but what you are doing is you are replacing the other atom by different atoms, for example hydrogen, deuterium, oxygen, chlorine. So as you are increasing the size, that means previously there was hydrogen, and I have already said that it depends upon the lighter object. So hydrogen was the lighter object, it is basically the lightest object, the wave number was very high. You replace it by deuterium, deuterium size is more, wave number decreases. Oxygen, it is more heavier, decreased. Chlorine, more heavier, decreased. So this is the concept. Vibrational frequency depends upon the lighter object mass. Next, type of vibration being observed. Okay, so you can also understand this, that vibrational energy would be dependent upon, or vibration would be dependent upon whether stretching is taking place or bending is taking place. Understand this, that it is always that the stretching vibrations would require more energy, or would be done at a lower wavelength or higher wave number, because it is always easy to bend a molecule rather than stretching a molecule. Therefore bending would be easier. If bending is easier, that means it can be done on a higher wavelength, whereas when I talk about stretching vibrations, they are difficult to create. If they are difficult to create, they can happen on lower wavelengths or higher wave numbers. Okay, I believe you would have understood this. Let us move on to the next topic, that is infrared absorption intensity. Okay, so the absorption, basically how much absorption or how much infrared absorption can take place, it depends upon the concentration of the molecule in a sample. Now understand this, suppose this is a test tube, and inside this test tube, suppose there is a molecule X, and this molecule X has the ability to absorb the infrared radiation. So as the amount of the molecule X in this sample is increasing, then automatically there would be more infrared absorption. Magnitude, next thing is magnitude of the dipole. So if the molecule is increasing over here, intensity of absorption would increase. Magnitude of the dipole moment, that means change in the dipole moment, as I have already explained you what is meant by change in dipole. As the change in the dipole moment is higher, intensity of absorption is also higher. So there are two features on which the infrared absorption depends. First is the concentration of the molecule, second is the magnitude of the dipole moment. Okay, now infrared absorption and chemical structure. Now as I have already said that what is the purpose behind doing infrared radiations. So the sole purpose is to identify the functional groups. What is the functional group that is present inside a given molecule? This is what we absorb. Basically we are trying to decipher the structure of a compound. So in that process only we are predicting the functional groups. We can predict the functional groups based on the infrared radiations or infrared absorptions. We can check out the peaks and we can check out the wavelengths at which these peaks are occurring, right? So infrared radiations can occur between 400 to 650 centimeter inverse. Now this infrared radiation can be divided into two portions. First is the functional group region and the second one is fingerprint region. Functional group region and fingerprint region, I will be showing you this. Functional group region lies from 4000 to 1500 centimeter inverse. Fingerprint region lies from 1200 to 700 centimeter inverse. Now what is functional group region? Understand this, that functional group region will tell us that what functional group is present. And we know by standards that suppose this particular bond is present, carbon hydrogen bond is present, so the wavelength at which it should be present would be around this one. So 3200 to 2800. If C double bond O is present, then 1800 to 1600. See, we already know through previous experiments that if this bond is there, it will show a peak at around this wavelength. This we already know. So this kind of information can serve as diagnostic markers. We can easily check that at which wavelength the peak is present, and depending upon that information we can predict the functional groups. Okay, now let us talk about the fingerprint region. Now fingerprint regions are very complex and confusing to interpret. Why I am saying that? Because the bonds carbon oxygen, carbon carbon, carbon nitrogen, carbon hydrogen, that means any kind of bond, the information is present in the fingerprint region. Just like each individual has its own fingerprint, this region or any compound, for instance, any compound would have its fingerprint region different from the fingerprint region of another compound. Okay, so you can predict so easily using the fingerprint region that which molecule it can be. However, it is very confusing and difficult to interpret, and it gives you information about each single bond. So therefore it is different for each molecule. You can compare two molecules also on the basis of fingerprint region. Okay, so these two regions are present in the infrared radiation. Let me just show you quickly. I showed you this. Okay, so this is hexanone. Okay, so you can see over here, if I say this is carbon, 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 and this is also carbon. This is hexanone. I have taken this photograph from Pathfinder. So in this you can see that on y-axis transmittance is present, and on the x-axis wave number is present. As I have already said, wave number is just inverse of wavelength. For the proportionality to energy, we wanted something to be directly proportional to energy. Wavelength is inversely proportional. We wanted something to be directly proportional. That is why wave number concept was introduced. Now understand this, that at 100 you can see that there is a peak somewhere around 3000. Okay, if you see this is 3000, there is a peak somewhere around 3000, and I have already said over here, if you see, so over here if you see, then CH stretching takes place around 3200 or 3000. Okay, so if the bond is present like this, then you can easily predict that it might be CH bond, and depending upon the intensity of the peak, you can also understand that how much of this is present, what is the amount of this present. Look at this, 1716, around 1716 there is C double bond O bond. Okay, and over here if you look closely, then this is fingerprint region. You can see that there are so many peaks in the fingerprint region. That is why I said that analyzing this can be a nightmare, would be difficult, but it can give you far more information. This is the functional group region. Okay, so in this way there are multiple peaks that you can easily analyze using the standards, and you can compare your work or your amount or your molecule with molecules that have already been deciphered for predicting the functional group. So this was all about infrared radiations, infrared absorptions. If you have liked the video, please hit the like button, click the subscribe button also, and do not forget to share this video with your friends so that all of you can learn together. Thank you so much and have a good day.